Chapter 15 is our last test. It's the chi-square test, and we're only doing the one that's for the goodness of fit, not the test for independence. So that's a two-factor chi-square, two independent variable chi-square. We're only doing the one independent variable chi-square. It's considered a non-parametric test. That means it doesn't have any means or standard deviations. The data doesn't lend itself to that, so you don't have any population parameters to compare it to. Generally, the independent variable is a categorical variable, meaning it has levels that are categories or nominal in nature. The dV is a count of the number of incidences in each of the categories of the IV. So what you're really testing against is the expected distribution of the count if the null is true. So is that an even distribution or is it some other kind of distribution? If the null is true, and then you compare what you actually get, the observed values they call it, to that expected distribution. So your question would be the same. Just plunge right into an example. Is there a preference in car color? So what you'd be doing is presenting people with different car colors and then asking them which one they would prefer. And so they tell you, and you mark a tick mark under the color that they pick. Conversely, you could go out and just observe, have a set a category number of car colors and go out and just the ones you observe, then put a tick mark under the category that you're observing. So the kind of data you'd see, and car colors kind of had to read there, but I put my variable car color and I've looked at black, white, yellow, and red as to what people might prefer. And the observed data is what I've actually gone out and collected. So I went out and observed 40. You can pick any number you want, but generally what you'll find is that it'll be nicely distributed among the four categories. So I went out and observed 40 vehicles, or asked 40 people what they preferred, and I found that there were 15 black, 5 white, 3 yellow, and 17 red. Now what goes in the bottom row is what is expected if the null is true. So you're basically thinking, if my experimental hypothesis is that there will be a preference in car color, the null would say there won't be a preference. And the way that shows up numerically is that they should all be the same, in which case if I observe 40, I should see 10 in each category. The thing I calculated in terms of the initial calculation of the data is I'm going to take observed minus expected right here, so the difference. So if the observed value exactly equaled the expected value, we should see all these O minus E values being 0. But what we have is they're not 0. Some are more than we observed more than we expected, and some we observed less than we expected. So that's what the values are here. So that's all we need to do for the initial setup. Put the hypotheses down. Again, we took the question, rephrased it as a prediction. There will be a preference in car color, and the null is there will not be a preference in car color. So again, they're done similar to what you've done with hypotheses before. One difference is there's no symbolic form of the chi-square. You don't have that here, so you don't need to worry about it. So I found the critical value here using the alpha 0.05. Degrees of freedom is C minus 1 instead of N minus 1. It's the number of categories minus 1. So we're not based on the number of observations or people, it's based on the number of categories. So you look up alpha 0.05, 3 degrees of freedom, and chi-square is only a positively skewed distribution, does not have a left tail because it is a square, so that it is really a chi-squared distribution. So your critical value is marking off the region only to the right, so we need to be a value greater than 7.81. Here's the chi-square equation. It's sum of the observed minus expected squared over the expected. So the numerator makes sense. We're taking the difference between the observed and expected. So you might imagine that chi-square at a minimum should be 0, because if the observed equaled the expected, the difference would be 0. We square them because we're not interested in which direction it is, but the magnitude of the difference. And then we divide by expected. So the reason we divide by expected is if I'm holding a dinner party, this example I give you in the book, for 10 people, but 20 people show up, the difference is 10, but I'm unlikely to be able to have enough food for 20 people because I was only prepared for 10. So it's a much bigger impact. If I'm throwing a dinner party for 100 and 110 show up, it's still a difference of 10, but the impact is considerably less. I'm likely to have food for 110 people if I have food for 100. So this is why we divide by the expected value, because it tells us the impact of that score. Well, step 3 is pretty short compared to ANOVA especially. So we have our equation there. And now what we put in are the values that we did O minus E. These are the values from that previous data summary. 5 minus 5 minus 7 and 7. And we're squaring those in the numerator and then dividing by the expected value. So if you work that out, you get 14.8. And that's the end of step 3. Step 4, again, the 3 things I'm looking for is reporting the chi-square as it would look in a journal, whether you reject the null, and then what that conclusion is. So we have chi-squares reported a little differently. In parentheses, you put the degrees of freedom, which is the 3, but you also put the size of the sample, which is 40. The value, it's equal to that you calculated in step 3, and then whether it beats the critical value or not. So p less than 0.05 because we beat the critical value. We reject the null and say there is a preference in car color. But unlike ANOVA, there's no post hoc to find out exactly where those differences lie, because all it's really saying is that it wasn't equal, it's not equal, so some cars are preferred. So if you look back at the data, you'd say, well, it looked like the black cars and the red cars are more preferred over the white and the yellow cars. But there's not any significant differences or anything stated there. There's one other thing that you could get that's different with chi-square is sometimes they will give you percentages. So like percentages of the different categories. In this case then your expected values are based on the percentages and not evenly distributed. So you'd have to say if I had X number of observations, then I would take the percents of those. So if I had 3 categories and the preferences were as follows. This example, I have 3 categories, it doesn't matter what they are, 1, 2, and 3, but they're not evenly distributed to begin with. So it may be a population, like one of the examples in the text is the ages of drivers. Well, that's not evenly distributed. So in this case, in category 1, it's 25%, 60% in 2, and 15% in 3. So if you went out and observed 300 values, or whatever it is category you're looking at, you would have 25% of 300, which would give you 75, 60% of 300, which gives you 180, and 15% of 300 gives you 45. So then these would be your expected values, and you would compare those to the observed values that you actually have for the count. That's the only difference in one of the problems you have to do in the text. So here I've done the effect size. This is the one we're using, is the W, which is square root of chi-square over n. Remember, chi-square is already squared, so don't square it in there. So it's equal to our 14.8 from our problem divided by 40, and that comes out to 0.61. The values for whether it's a small, medium, or large effect are 0.1 is small, 0.3 medium, 0.5 is large, so we have a large effect here. So it's a substantial difference from what we were expecting by chance.